What if the three-dimensional world you live in, your body, this room, the entire universe, is actually a projection? A hologram beamed from a two-dimensional surface at the edge of space. That's not science fiction. That's what Leonard Susskind and Gerard Hooft proved in the mid-1990s, and it means reality is fundamentally stranger than anyone imagined. The universe might have one fewer dimension than it appears to have. This is the story of the holographic principle, the idea that turned physics inside out. To understand why Leonard Susskind came to believe that three-dimensional space is an illusion, you need to know one thing about him. He doesn't give up on puzzles. Susskind grew up in the South Bronx in the 1940s. His father was a plumber. Nobody in his family had gone to college. When young Lenny told his father he wanted to be an engineer, his dad looked at him and said, "You ain't going to be no engineer. You're going to be Einstein." That's the kind of confidence that shapes a career. By 1994, Susskind had already made his mark. He'd co-discovered string theory in 1970. He'd spent years thinking about black holes and quantum mechanics. And he was in the middle of what would become a 28-year battle with Stephen Hawking over whether information is destroyed when it falls into a black hole. But the holographic principle, the idea we're about to explore, might be his most mind-bending contribution to physics. Because if Susskind is right, everything you think you know about space is wrong. Here's the question that started it all: how much information can you store in a region of space? Your instinct might be, well, it depends on the volume. A bigger box can hold more stuff, more atoms, more particles, more information. That's obvious, right? Wrong. In 1993, a Dutch physicist named Gerard Hooft, who would later win the Nobel Prize, proposed something radical. He suggested that the maximum amount of information you can store in a region isn't determined by its volume. It's determined by its surface area, the boundary, the walls of the box, not the space inside. That doesn't make any sense. How can the amount of stuff inside a room be limited by the size of the walls? But Hooft had a reason for thinking this. He'd been studying black holes, and black holes, it turned out, were hiding one of the deepest secrets in physics. Let's talk about black holes for a minute, because this is where the story really begins. In the 1970s, Jacob Bekenstein and Stephen Hawking proved something shocking: black holes have entropy. Entropy is a measure of disorder, or more precisely, it's a measure of how many possible microstates correspond to a macroscopic configuration. The higher the entropy, the more information is hidden inside. For normal objects, entropy is proportional to volume. A bigger object can store more information because it has more atoms, more possible configurations. But black holes are different. Bekenstein and Hawking showed that a black hole's entropy is proportional to the area of its event horizon, the surface that marks the point of no return, not the volume inside the surface area. Think about that. You've got this massive three-dimensional object, a black hole that might contain the mass of 1,000,000 suns, and all of its information content is determined by a two-dimensional surface. It's like saying everything inside a sphere is somehow encoded on the surface of the sphere. Gerard Hooft looked at this result and asked, what if this isn't just a weird property of black holes? What if this is a fundamental rule for all of space? In 1993, Hooft gave a talk at a conference proposing what he called the holographic hypothesis. He argued that the three-dimensional world we experience might actually be encoded on a two-dimensional boundary, like a hologram. A hologram, if you've ever seen one, is a two-dimensional surface that creates the illusion of three-dimensional depth. But Hooft was saying, maybe our entire universe works the same way. All the information about particles, forces, fields, everything might be stored on a distant two-dimensional surface, and what we perceive as three-dimensional space is just a projection. Most physicists thought this was crazy. But Leonard Susskind, sitting in his office at Stanford, thought it was brilliant, and he was going to prove it. In 1994, Susskind published a paper titled "The World as a Hologram." It would become the most cited paper of his career, over 400 or 500 citations and counting. Here's what Susskind realized. If you try to cram too much information into a region of space, something catastrophic happens. You create a black hole. And once you've got a black hole, the maximum information in that region is determined by the area of the event horizon, not the volume inside. This suggests a hard limit. The maximum entropy. The maximum information in any region of space is proportional to the surface area of that region, measured in units called Planck areas. 1 bit of information per Planck area. Let's break that down with an analogy. Imagine you're writing a novel and you want to store it in a box. Your instinct is the bigger the box, the more pages you can fit inside. Volume determines storage capacity, but Susskind's holographic principle says no. The maximum number of pages you can store in the box is determined by how much you can write on the walls. If you try to pack more information inside than the surface area allows, the box collapses into a black hole, and then you're back to the surface area limit anyway. It's as if the universe has a fundamental rule: information doesn't live in the bulk of space. It lives on boundaries. But here's where it gets even stranger. If information is fundamentally stored on two-dimensional surfaces, that means the three-dimensional world we experience, atoms, stars, galaxies, your own body, is a kind of illusion, a holographic projection. Susskind described it like this in his paper. Particles in three-dimensional space might just be shadows cast by information encoded on a distant two-dimensional screen. Now, this doesn't mean we're living in the Matrix. This isn't saying reality is fake. It's saying that the fundamental description of reality, the most basic, complete account of what's really going on, might be written in one fewer dimension than we experience. Here's an even weirder consequence that Susskind worked out. If you have a particle moving at low energy, it behaves like a tiny point, just like we're used to in everyday physics. But as you give that particle more and more momentum, more and more energy, it starts to grow. Above a certain threshold called the Planck scale, particles don't get smaller, they get bigger. Why? Because at high enough energies, you're approaching the limit where information density maxes out, and to avoid creating a black hole, the particle has to spread out. Its size becomes proportional to its momentum. This is completely backwards from how we normally think about particles. In quantum mechanics, higher momentum usually means smaller wavelength, a more localized particle. But in a holographic universe, the opposite happens at extreme energies. Susskind also worked out the connection to string theory. In string theory, particles aren't points, they're tiny vibrating strings. And Susskind showed that the holographic principle fits naturally with string theory. Strings can grow with energy in exactly the way the holographic principle predicts. Black holes, strings, holography, it was all connected. But perhaps the most profound implication is this: the holographic principle suggests that gravity itself might be an emergent phenomenon, not fundamental, just a consequence of how information is organized. If the fundamental description of the universe is written on a two-dimensional boundary and three-dimensional space is a projection, then maybe gravity, the force that bends and curves three-dimensional space, is just a kind of shadow, an illusion created by the deeper holographic reality. This is the insight that would later inspire Joan Maldaceno's arXiv correspondence, one of the most important discoveries in theoretical physics. Maldacena proved that certain quantum field theories on a boundary are mathematically equivalent to gravity in the bulk. Holography wasn't just a wild idea, it was real, and it all started with Susskind's 1994 paper. When Susskind presented the holographic principle at conferences in the mid-1990s, The physics community was split. Some thought it was one of the most profound insights in the history of science. Ed Witten, widely considered the smartest living physicist, sat in the front row at one of Susskind's talks with an expression that Susskind later described as trying to figure out if I was crazy or brilliant. Others were skeptical. The idea that three-dimensional space is a projection from a two-dimensional surface sounded too strange to be true. Where's this boundary supposed to be? At the edge of the universe, what does that even mean? But Susskind wasn't alone. Gerard at Hooft had reached a similar conclusion independently, coming at it from a slightly different angle. The two of them were building on the work of Bekenstein and Hawking, the black hole pioneers who'd first shown that entropy is tied to surface area. This wasn't a battle, it was a convergence. Multiple brilliant physicists working independently were all arriving at the same radical idea from different starting points. And then in 1997, everything changed. Joan Maldacena, a young physicist at Harvard, published a paper that would transform theoretical physics. He proved that a specific type of quantum field theory, living on the boundary of a space called anti-de Sitter space, is exactly equivalent to gravity in the interior. Same physics, different descriptions. It was called the Addis-CFT correspondence, and it was the first concrete mathematical realization of the holographic principle. Susskind's wild idea wasn't just philosophy, it was mathematics, and it worked. But here's the thing, even today, we don't fully understand the holographic principle in our universe. Maldacena's Addis-CFT works in anti-de Sitter space, a mathematical toy universe with different properties than our own. Our universe is expanding, accelerating into the future. It's what physicists call de Sitter space, and holography in de Sitter space. That's an open problem, one that Susskind himself is still working on, even now in his mid-80s. The holographic principle also raises deep philosophical questions. If three-dimensional space is a projection, what does that mean for our experience of reality? Are we conscious beings made of atoms and molecules, just patterns encoded on some distant boundary? Susskind has argued that this doesn't change the validity of our experiences. The holographic description and the three-dimensional description are both real, just different ways of talking about the same underlying physics. It's like a book written in two languages. The story is the same, but the words are different. Still, there's something deeply unsettling about the idea. We're used to thinking of space as fundamental, the stage on which physics happens. But the holographic principle says no, space might be emergent, derived, a projection from something more fundamental. And if space isn't fundamental, what else isn't? So what does the holographic principle actually mean for our understanding of reality? First, it suggests that information is more fundamental than space. The universe isn't a three-dimensional box filled with stuff. It's a two-dimensional information storage system that creates the illusion of three-dimensional depth. Second, it hints that gravity might not be a fundamental force. If space itself is emergent, projected from a holographic boundary, then gravity, which is just the curvature of space, might also be emergent. This has huge implications for quantum gravity. Maybe we've been thinking about it all wrong. Maybe gravity isn't something you quantize directly. Maybe it emerges naturally from a holographic quantum theory. Third, the holographic principle places hard limits on how much information can exist in a region of space. And this has consequences for black holes, cosmology, and even quantum computing. You can't pack infinite information into finite space. Nature has a maximum density, and that maximum is written on surfaces, not in volumes. The holographic principle has also reshaped how physicists think about string theory. In the late 1990s and early 2000s, string theorists were obsessed with Addis-CFT, the first concrete realization of holography. It gave them a new tool. You could study quantum gravity by studying quantum field theory on a boundary. Hard problems in one description became easier in the other. Even today, arXiv is one of the most active areas of research in theoretical physics. Physicists use it to study everything from quark-gluon plasmas to quantum entanglement to the information content of black holes. But the biggest open question remains, what's the holographic description of our universe? Maldacina's arXiv works in anti-de Sitter space. But we live in a universe that looks more like de Sitter space, expanding, accelerating. And holography in de Sitter space is budoai harder. Susskind has spent the last several years working on this problem. He's published papers with titles like De Sitter Space Has No Chords and 3 Impossible Theories exploring the deep challenges of doing holography in an expanding universe. It's possible that the holographic principle, as beautiful as it is, doesn't apply cleanly to our universe. Or maybe we just haven't figured out the right formulation yet. Either way, this is one of the biggest unsolved problems in theoretical physics. But here's what we know for sure: the holographic principle works. It's not speculation. In anti-de Sitter space, holography is mathematically proven. And the idea that 3-dimensional physics can be encoded on a 2-dimensional boundary has become central to how physicists think about quantum gravity. If you'd told physicists in the 1980s that space itself might be a hologram, they would have laughed you out of the room. But today, it's one of the most successful ideas in theoretical physics. And it started with Leonard Susskind staring at equations about black holes in his Stanford office, asking what if space isn't fundamental. Leonard Susskind is 86 years old now. He's been doing physics for more than 6 decades. He co-discovered string theory. He fought a 28-year battle with Stephen Hawking over black hole information and won. He proposed the string landscape, the Gerard-EPR conjecture, the fast scrambling theorem, the complexity equals action program. But when you ask physicists what Susskind's most important contribution is, a lot of them will point to the holographic principle. Because this idea that 3-dimensional space is a projection from a 2-dimensional boundary isn't just a solution to a technical problem in quantum gravity. It's a complete reimagining of what reality is. For thousands of years, humans have believed that space is the fundamental stage on which the universe unfolds. Empty, passive, 3-dimensional. The holographic principle says wrong. Space isn't fundamental, it's derived. It's a shadow cast by information living on distant boundaries. And if space isn't fundamental, what is? Maybe information, maybe quantum entanglement, maybe something we haven't discovered yet. Susskind is still working on these questions. He's still publishing papers, still teaching at Stanford, still pushing boundaries. At 86, he's thinking about de Sitter holography, the hardest, most unsolved version of the problem. Will we solve it in his lifetime? Maybe, maybe not. But that's what makes physics exciting. The holographic principle reminds us that reality is far stranger than common sense suggests, and every time we peel back another layer, we find something even more bizarre underneath. If you want to dive deeper into Susskind's work, our next video will explore his battle with Stephen Hawking, the black hole war that lasted 28 years and ended with one of the most dramatic concessions in the history of science. The holographic principle played a central role in that war, and the stakes couldn't have been higher: the survival of quantum mechanics itself. 3-dimensional space might be an illusion, but the journey to understand why, that's as real as it gets.